Hello, we are talking about optimization today. So what you have in front of you are the steps to optimization, and what I would like for you to do right now is go ahead and read 1 through 3 to yourself. So pause the video and read 1 through 3 now, please. Now, I wanted you to read 1 through 3 because I actually should have added something to 3, so I'm going to kind of call this a 3.5, but it's really kind of added to this right here. We're going to use substitution to create one equation, and this one equation will have one variable. So this is similar to related rates, where we had to take a word problem, create an equation that we were going to work with, and then we needed one variable with that. So it's the same idea that we've done with related rates, except we're doing it with optimization. So what I'd like for you to do now is pause the video and read 4 through 7. So pause the video now, please. Okay, so what we're going to do is using these steps, we're going to solve this example problem. So we've been asked to design a 1 liter or 1,000 centimeters cubed oil can shaped like a right circular cylinder. And what are the dimensions that will use the least material? So we provided you with 2 equations that we should know from geometry. So here they are for us. So step 1, understand the problem, read the problem carefully, and identify the information you need to solve the problem. So for this example, for step 1, I was given that the volume is 1,000. We're going to go ahead and use cubic centimeters because I would measure a radius and a height in centimeters, and the question is asking for what dimensions will I use for my right circular cylinder, and I would need to know the radius and the height. So the formulas I have are the volume and the surface area. I'm just going to call that area. Next, we need to read step 2. Develop a mathematical model of the problem. So what I have in step 2 is I have a right circular cylinder, and with the cylinder I have a radius and I have a height, and I need to let a variable represent the quantity to be maximized or minimized, and I'm minimizing the material. The material is the surface area of this cylinder, so I'm trying to minimize the area, which is 2 pi r squared plus 2 pi rh. So that's step 2. Step 3, make a second equation with the constraints given in the problem. So step 3, we know that the volume has to be equal to 1,000. So I'm going to set the volume equation, pi r squared h, equal to 1,000. So that's set. My volume is going to be set at 1,000. The next thing it says in step 3, then get the equation in terms of one variable. So I have a choice here. I can either solve for h or I can solve for r. In looking at r, eventually when I solve for r, I'm going to have to take a square root. I really don't want to. So instead what I'm going to do is I'm going to solve for h. So to do that, I divide by pi r squared. So that gives me that my h is 1,000 divided by pi r squared. That's my h. So I've done step 3. Now I need to do step 3.5. Use substitution to create one equation with one variable. Now what I want to minimize is the surface area. So I'm going to go back to my surface area, and wherever I see an h, I'm going to replace it with 1,000 divided by pi r squared. So I've replaced my h, and what I'm going to do now is I'm going to simplify this a little bit just so it's a little easier to work with. So I have 2 pi r squared plus 2,000 pi r over pi r squared. And that actually works out nice because I can simplify that a little more. So that's the same as 2 pi r squared plus, let's see, my pi's, they simplify. An r on the top and my r's on the bottom simplify so that I have 2,000 divided by r. And lastly, what I want to do is I want to write this in calculus-friendly terms. So 2 pi r squared plus 2,000 r to the negative first power. So that's my step 3.5. I now have one equation in terms of one variable, and I am trying to minimize the area, which is what my equation represents. Step 4, determine the domain of the function. This is a little tricky because this domain is a little hard to figure out. And so sometimes you're going to have a domain and sometimes you won't. And what I was thinking about with this domain is what's considered reasonable. So the domain is for R, and so R has to be between 0. Again, if it can't really be 0, so I'm going to put a parenthesis there, because if I had a radius of 0, I would have no cylinder. Likewise, if I had a height of 0, I would also have no cylinder. So coming back to my equation that I was working with in step 3 that I had in red, I'm going to circle it blue right now. I know that this has to always be true. I have to have 1,000 as my volume. So what I did to find sort of the largest that my R could be, I picked something small that my H could be. And we're talking centimeters. So really I probably could have used a height of 1 centimeter to do this, because obviously that radius is going to make it very short and very, very fat. But what I did is I used H as 0.1. Let's just make sure that we are out of the realm of reasonable. And when I did that, I plugged in H was 0.1 and I figured out what R was. I got 56 and change. So I'm going to say that my radius has to be somewhere between 0 and 60, and that's being very generous. So the 60 should probably never happen in the real world. So that's my estimated domain. Step 5, you find the critical points and the endpoints and find where the derivative 0 and fails to exist. So step 5, I need to find the critical points, which means I need to find my derivative. So I find the derivative of a, and again a is over here. So that derivative is 2 pi times 2r plus 2,000 times negative r to the negative 2. And of course I can simplify this, and I have 4 pi r minus 2,000 divided by r squared. And to find my critical points, again, from last class, we need to set our derivative equal to 0 and also find where my derivative does not exist. So I set it equal to 0. I add the 2,000 over r squared to the opposite side of the equation, and then basically what I'm going to do is cross multiply. And I have 2,000 is equal to 4 pi r cubed. And then I want to get r by itself, so I divide by 4 pi. And then I'm going to take the cubed root of this. And of course I could simplify this into 1,000 over 2 pi. It's messy enough, doesn't really matter. So that's what my radius would be in centimeters. That is the critical point. That is where the derivative is equal to 0. Also, the derivative is undefined when I have a 0 in the denominator. And if you look back up here, that's going to happen when r is equal to 0. However, when r is equal to 0, we have no cylinder. So r equals 0 is not really relevant. Basically what I found, I have found places to look for this minimum. And the places are r equals 0, which doesn't make any sense, r equals 60, which makes a really, really short, really fat cylinder, and then I'm looking also at my critical point, which is this. So step 6, We are now going to use the second derivative test. Now, if you so chose, you could do the first derivative test. The recommendation is second derivative test. It usually makes things a little bit easier. And again, you could use first derivative test if you wanted to. So step 6, second derivative test. So I'm going to take my second derivative. So again, my first derivative is over here. So that's going to be 4 pi and then plus 4,000 r to the negative 3. So remember that what this was 4 pi r minus 2,000 r to the negative 2. And so when I take that derivative, I multiply negative 2,000 by 2, giving me my positive 4,000. So from here, I'm going to use my second derivative test. My second derivative tells me concavity. So I should be able to plug in my r, which is the cubed root of 2,000 over 4 pi, into this equation and decide whether the second derivative is positive or the second derivative is negative. But let's take a look first. So what I have for my second derivative is I have 4 pi. That thing is positive. It's a positive number. And then I'm going to take plus 4,000 divided by r cubed, because my exponent was negative. And if r, we've already determined our domain for r, coming back to step 4, r has to be a positive thing. We can't have a negative radius. So 4,000 divided by r cubed is also a positive thing, which means my second derivative is always positive, which means a is always going to be concave up, which means whenever I have a critical point, that's going to be my minimum. So for this point now, we know this critical point at the cubed root of 2,000 divided by 4 pi, that has to be the minimum of my area. So step 7, I need to interpret what I have and answer the question. Then I should answer this in a sentence. So in step 7, the least amount of material and that least amount of material happens when r is the cubed root of 2,000 divided by 4 pi. That says 44, sorry. Divided by 4 pi centimeters. I went ahead and I picked up my calculator and I worked that out, and that came out to be roughly 5.4192 centimeters. And we also need a height because we needed the dimensions. So all I did was I took the height and the radius, and I plugged it in. I'm going to move my screen for a moment. I plugged it into step 3, circling in red. I square the radius and take 1,000 divided by pi times the radius squared. That gives me my height, so I'm literally just going to plug in like that. So that's going to be 1,000 over pi times the cubed root of 2,000 divided by 4 pi squared. And I did calculate that on my calculator. I got 10.8385 centimeters. So we have answered the question. We have identified what dimensions use the least amount of material. At this point, we could check our answers, because if I use this radius and I use this height, I should get a volume of 1,000. So a good thing to do if you have the time would be to take these values, plug it back into your volume equation, because we know that the volume has to be 1,000. And when you plug this in, you should get that. Which I have done, and I think this one is correct. So this is optimization, and we will continue working on optimization next class. I hope you have a wonderful evening.